Hi, my name is Bart Romani. I'm Emeritus Professor in Biomedical Image Analysis at Eindhoven University in the Netherlands. I had a long career in education and research, and now retired, I'd like to take the opportunity to take you on a tour on how I programmed with Mathematica, which I consider a true 21st century coding, and I do this on the Raspberry Pi. It's an environment which is quite nice because the Raspberry Pi is amazingly nicely developed. Let me start with something remarkable. We have images of Python code here, and clicking this hyperlink opens now a browser. Let's make it a little bit smaller. And now what we see is typical screenshots from Python code, and what's immediately clear is that it is quite dull. No images, no formulas, no mathematical stuff. It is just plain text. And this reminded me to how I used to program long time ago. In 1999, we had WordPerfect. Many of you don't know this, but if you look at the screenshot of WordPerfect so many decades ago, it looks like this. This is how I typed my PhD thesis. It's very old-fashioned. And it's amazing, but the programming today, the command line interface, is still in this style. And if you look on the YouTube math tutorials, then we see that this is images from the YouTube tutorials. Many people still use the whiteboard because it's difficult to make formulas and mathematical and scientific notation on your computer. It's still not there. So many people just use the whiteboard. And now let's have a look at Mathematica on the Raspberry Pi. You see a notebook here right now. This is the Raspberry Pi. So everything that you will see is on my own Raspberry Pi. The notebook that I show here can be downloaded. You see it just right here. If you go here, automatically the browser opens, and on your Raspberry Pi, you see it right here. It will be downloaded, and if you look in the downloads directory, you see it. I had it already there, so there's now a one version. I have one extra. But this is how easily you can get the notebook. Well, the Raspberry Pi is remarkably powerful, and it runs Mathematica really well. And everything you will see is on the Raspberry Pi 5 is 4 GB, 64 GB SD card. I have Debian Bookworm 64-bit with the Raspberry Pi desktop. And my version is, let's see what is the version, 13.3.1 for Linux ARM. Mathematica is free on every Raspberry Pi, so it's made by Wolfram, so wolfram.com has a website, Raspberry Pi, and most of the Pi users will know it. And you see here clearly Wolfram language and Mathematica free on every Raspberry Pi. So how to install it? You can download the installation script, make it executable, and then run it. But there's an easier way to install it. That is, just go to Preferences and then Recommended Software. And it will look for finding packages. And once it has these packages, you go to Programming, and you see Mathematica here. And if you just make this indicated, then it will install. And that's all you have to do. It's a big program, 1.4 GB, so it takes quite a while depending on your internet connection. But I like to show you a little bit of examples, and if you've never seen it, you may be surprised by the power of Mathematica. Actually, it looks a little bit like the 21st century we are used to with MS Word. I have Microsoft 365 installed on my Raspberry Pi. Indeed, you can now run all the nice Microsoft applications. So, for example, I start the Word application, and let's say I start with a blank document. And now I can do everything I can do on my laptop as well. And the Raspberry Pi is really fast. You see, I have all the style notations and colors and fonts, etc. So this is quite nice. I even have general templates. So for example, if I take this specific template, it loads it. And here you see what I mean with 21st century presentation. Colors, images, style, etc. And this should be in your code as well. That's exactly what Mathematica can do. We close all this. A little bit about me. You can read it yourself. I'm an emeritus professor, and actually Mathematica made my career. I was working with Mathematica from the very beginning in 1988, and I used it for research, education, and lots of my students and myself, we played with the concepts. Mathematica is, as no other language, a wonderful environment to discover and to play directly. This is a lot about how I loved to work it. You can read it on your own. And I like to straight dive in. What do I mean with 21st century coding? Well, it's pretty graphical. So images can be dragged into the code from web browsers or other programs. And this is now an manipulate, an image rotate over phi, and take all these surroundings and let phi run from 0 to 2 pi. And you see a lot of things. You see that I can use Greek symbols like the pi and the phi. I have images in my code. If I run this code, you see that I get an automatic Java applet generated by this function manipulate. And now I can directly rotate my image. And you see it's so smooth and it's so fast. And this is what I mean with century coding. If I want another image, let's say I want here another image, I just open a browser and I say I want now another image. I want a dog, and take images. And now you say, okay, I take this image and I say copy this image. Go back to Mathematica, put your mouse right here and just say paste, and now you have the image from the dog right into your code. So now, so easy is it to pick any image or whatever to read it from the net. You can also use manipulate and then do, we have the tiger here again, an image perspective transformation, and now we see the mathematics coming in. If I want to rotate my image, it's actually using this rotation matrix with the cosines and the sines. And this is another matrix, it's called an affine matrix. With this matrix I can zoom and shear and scale, and these matrices are multiplied with the dot operation. So this is a matrix multiplied with another matrix, and now you see directly the mathematics. And with manipulate, I can manipulate all these parameters. So I can change the alpha, of course that's the rotation angle. I can change the x, that is the shift left and right. Y is the shift up and down. S is the scale, that's the zoom factor. And A, B, C, and D are the affine transformations. So let's see what happens if I change them one by one. So A runs from -1 to -1, but it starts at 1. And it has the title on the bar X magnify. Let's just run it and see what happens. Now you see that all these settings here, they have translated in nice slider bars, and with this, you see, I have the X magnification. I can have the Y magnification in exactly the same way. I can have the rotation angle. So this is alpha, now it rotates around the origin. I can have the zoom. And no matter what I set, I have all the reset here. So with this simple thing, if I have a button here, when I click reset, it has the name reset, it puts back all these default parameters. So code, images, formulas, it's all integrated now. And you can do the same as you can do in Microsoft Office, many modern fonts. So for example, if I ask, and any system variable starts with a $sign. So the font families are indicated by a $sign. And another curious thing in Mathematica is that all the internal functions and variables, they begin with a capital. Your defined variables and functions begin not with a capital, with a small case letter. So what are these font families? Lots of them. It depends on how many you have installed, but all of these are now available in your code. And if I print here the styles, you see I have a very nice thing which I explain all later here. This is how you define a pure function in Mathematica. Style means print something, and something means that this is a slot, I put something in. Print, for example, the first one from this font families, and that's Allegria. Print it in a certain style. What is the style? Well, the font family is also font Allegria. So this means print the word with the font style, that same thing, and do it for all the font families. This means map, do it for all. All this I show you later, but now I want to show you just the possibilities. And here we have it, all these fonts. And I made this particularly. Notebooks were invented by Wolfram. You see, I changed the font. You can do the same if you have it here with format, and it's just like Word and PowerPoint, etc. You change the font here and pick any font you like. You can change the size and the style, etc. So it's just like we are used to. In terms of graphics, it's quite amazing what you can do. You know all these beautiful graphics from, for example, 3 blue, 1 brown. This is an example here on YouTube where he explains a complicated thing. And this is visualizing, oh sorry, here. And you see he's visualizing now a function x squared y, written by the way on the whiteboard, and he has a circle. But how does he make this? Well, he uses the program Manim. But if you study Manim, it's quite difficult. And if you make this yourself in Mathematica, all you have to do is say, okay, I want to plot this surface, x squared y is constant, together with the cylinder, x squared plus y squared is 1. And then make it a contour plot. And I put all kinds of nice things and have a dedicated YouTube movie explaining step by step what I do here. That I do not want axis, I do not want a mesh, I want so many plot points, I want to have a specularity, etc. And when you plot this, and it's actually a one-liner, you get very nicely, you get the plot, and you can directly see it in 3D. And this is on a Raspberry Pi, can you believe it? If you do this on a laptop, it goes way faster, but it is already quite fast enough. And if you want to see the cylinder, you just change the opacity. And now here we have the cylinder, and we can look inside, and you see we have the full 3D view, and the opacity of the cylinder can be interactively regulated. You can even regulate the intersection between the two, which are made into a tube. You can change the radius of the tube. So all of it is interactive now. And I made this in 10 minutes. Well, there are extensive function visualizations and data visualizations. So if you look in the data documentation, this is the documentation for function visualization, and it's very impressive. All the different plots that you know of, contour plots, slice contour plots, density plots, it's all there. Parametric plots, polar plots, revolution plots. It goes on, and all of them are very professional, very fast. You can tune any color, intersections, whatever, vector plots. You style them in different ways. And this is a really nice thing to look through. This is function visualization. Here we have data visualization. So if you look at the possibilities for data visualization, plot points, lines, stacked lines in log linear, list line plots, do it all in 3D. It's beautiful. And all of this is right there. So my recommendation is have a look, study them, and I go show them quite a few, but this is an overview lecture. I just want to point you the way that this exists, and it's really nice to learn, to study these tutorials. This is, for example, a bar chart 3D, and I want cylinders in my bar chart. So, well, what you do is just put a cylinder in. You say, put your chart elements and make them a cylinder. So this is the symbolic representation of a cylinder. Let's see what happens, what I do now. And now I get my bar chart, and you see it's beautiful in 3D, and it has cylinders. It's a very simple one. It has just the numbers 1 to 5, but you see how easy it is to actually create whatever you like. If I want to play a little bit with our globe, you say, okay, let's import an image from our planet Earth, and this is what you call a Mercator projection. And I like to fold it around a sphere and see if I can put this on top of the sphere. So what I do is I make a spherical plot 3D with a constant radius of 1, and I change just the u parameter from 0 to pi, and the v parameter. Actually, I should write here escape p escape, and then you write a pi, and this should also be escape p escape. This is the way how you write Greek letters. And now you see I can make a texture, and in the texture I just put the image here. And now let's see what happens. It put the texture on my surface, and I can take any picture and any surface. I could even take my own picture, but now you see how easy it is to make textured graphics. And on the Raspberry Pi it is so fast. It has a new graphics processor that you see all the 3D can now be directly, very smoothly animated. Mathematica is very precise. I have a beautiful number here. It's quite a complex formula, and you see it has square roots, it has power to the 1/3. And now in Mathematica, you really can write all these exponents, square roots, etc. How do you write a square root? Well, you say I have 2, you highlighted it, and then you press Ctrl 2, and there you have it. So, and if you want to say, I want to make this to the power of n, you say Ctrl Het, and then you say to the power of n. So subscripts and superscripts, etc. Well, I'll show you later how to do this step by step. This is called a piezo number, an amazing number. So let's define it. And you see it is now blue, but as soon as I define it, you see that it is the 37th operation that I do, and now piezo is black. It's known to the kernel. Let's ask for the numerical value. And again, you see this is a capital letter because it is a function from the factory, from Wolfram. And functions always have square brackets. So you see the round brackets, they are really only used in mathematics. So you cannot use them for anything else. And this is why they're more or less holy. They have been used for decades, for centuries. And you won't want to change them for anything else. So they're only used for grouping. And in functions, we use square brackets. So the numerical value is quite big, 10 to the something. So let's ask for a whole number of digits, 6,000. And here we go. It's quite a lot. And now we see something really remarkable. You see that there is an amazing amount of zeros coming up. And this is so special for the piezo number. And not so many programs can directly show you this. Mathematica can show it. This is quite amazing. I'm always puzzled, how can people find such an amazing thing? And this was already found before computers were available. Quite amazing. If you have this formula, you want to use it in some document, you want to, let's say, use the LaTeX form, well, you can just say, make the TeX form from piezo, and then make it into a string. So you see, it's really English that you use. You say TeX form and make it a string, and we call that LaTeX. And here we have it. Put it in your LaTeX file, and it will directly make this number. If you want to go the other route, you say, well, I have LaTeX, which is a TeX form, and I want to make it an expression again. Well, you use the function toExpression. And there we go. So you can go back and forth very easily. Everything is interactive. So if I have this same bar chart, now I multiply it with alpha, you see that I can immediately change the alpha, and with a very simple thing you can now make any animated graphic or plot or whatever overview of your results, but they play. You can really see what happens. Any variable can be interactively manipulated, even in formulas. So suppose I have this formula here, expand x plus y. Let's do expand for x plus y to the power of 2. Well, you all know from high school that you get this, but now you want to make this n much bigger, and we let n run from 1 to 100, but I cannot have n 1/2, etc. So I take in steps of 1. This is the last argument. And now the manipulate makes again a Java applet, and now I can do interactive algebra. So, and you see it's really fast. So even if I go to 100, and this runs on a Raspberry Pi, Mathematica is really fast, and it does an excellent job. You see how beautiful it is. If I click on the plus here, you see I can see exactly how big is the n. You can even let it run automatically. So if you have a variable that you want to make a movie of, you let it run automatically. You can faster, slower, forward, backward, everything is possible. Interactive always also means, and let me first show you this, I have now a function here that is using a so-called locator. In other videos I'm going to explain exactly what I do here. But in a sense, you see, it is an interpolation. And I have points here, and every point, which is a locator, I can move. So you see, I can move them, and this is the interpolation of the function that goes through these points. So if I make the interpolation order 0, you see, I get nearest neighbor interpolation. So that is just a step function. And you can move all the points. If I make the interpolation 1, and again I can open this, and if I make it 1, you see I have linear interpolation, so there are now straight lines. And you see there's a nice tooltip that shows me what is the function. If I go to second order interpolation, if I go to here, second order, you get parabolic pieces. But the nice thing is that if you press Ctrl Shift click, you get another one. Sorry, Ctrl Alt. So I can add more points, and each point can be moved, but I can also, with Ctrl Alt, remove these points. So adding and putting points is all interactive. And now you can see that, for example, if you make a very high order interpolation, you get all these overshoots. And this is exactly what is meant by, here you see that this is overfitting of the data, and you can now very nicely see what happens if you take a too high order and the points are just in a particular order. You immediately see what happens. And this visual playing with code is for me the essence of modern 21st century computing. This is another one on image processing, and I use now the image of Mona Lisa, and now I'm going to do a transformation, not an interpolation, but I go do a radial basis transform. And that's an interpolation that takes points in an image. Let me just show you what it is. Not going, but you see I have a locator again, so I'm going to put the locator here, and now you see the locator is a point. You see I have made the appearance of the locator. It's a graphics object in red from a point at the origin. And I have put quite a number of them in the eyes, on the nose, and now I can change the position of the nose. And I can change the position of all the other points. So I can let her smile. And this is so fast, Mathematica is so fast, that because you have to calculate hundreds or even thousands of new pixels and all the points in between, even on the Raspberry Pi, I can do this interactively. This is really nice. The code was written by Marcus van Amsik, who did a PhD in my group, a truly Mathematica expert. He was also as a postdoc, and he was an outstanding guy in Mathematica, and he's now leading the image processing group at Wolfram Research, and was very proud to collaborate so many years with him. If you're on a Raspberry Pi and you're into 3D printing, then you know you have these endless molds. This, for example, is a nice website that has beautiful models. You can find thousands of them all over the place. For example, here you have a gear set. Well, all you have to do in Mathematica is you import directly from the website, and in this case it's a zip file, and you see it is here .pli. So let's import this zip file. It comes directly from the website. It will take a while because it has to be unzipped, and now directly you can see in 3D what is this. You can convert it into STL, send it to your printer. Mathematica can read lots of formats. There's another one I'm going to show. But if you see how many input formats it can read, it's amazing. Everything almost that exists can be read into Mathematica. So STL, PLI, well, you name it. All the compression formats, all the image processing formats, and exactly the same for the export formats. So if you need to convert one data set to another one, you use Mathematica. I can show a bit on scientific notation, and this is what the notation actually says. Control B, as we all know from other programs, give you bold, Control I italic, but Control head gives the superscript, Control underscore the subscript, Control slash gives you the division, Control 2 the square root. So these are all modifications of a letter, and now here you create letters with escape P escape gives you the pi, escape F escape gives you the phi, etc. for all the Greek letters, escape euro, etc. Well, read this on your own. If you really forget it, there is a nice, in the documentation center, all of them are there, and here you have all the keyboards shortcuts, and to the right you see all the keyboards, and it's endless, but the most important ones you see here. If you forget it, you can also use palettes, and here we have the basic math assistant, and here you see, for example, if you click advanced and you want to implement something, for example here, I want to implement an integral, you click here on the integral, and now you see I want to make the integral, so from infinity, minus infinity, I say minus, and then escape, inf, escape. And this is how you make escape, inf, escape. And then you can just say whatever you like. For example, E is escape, double E, and then to the power minus x square, you integrate it to x, and then you run it. So this is the way you implement all kinds of mathematical notations, and it's quite easy. There's all kinds of cheat sheets, but let's go on to the main lines. Neural networks, for example, so modern, and Mathematica has an amazing environment for that. This struck me that it is so beautiful. If you have all these layers, and I have a whole set of layers here, batch normalization layer, tangent hyperbolic layer, logistic sigmoid layer, all these layers are available. And I put them in a specific, very complex layout. I draw that on paper, and I said, now, this is how I want this total layer should have its output to this batch normalization layer. And all of them has a number. This is number 1, that's number 2, that's number 3. And in Mathematica, all you have to say is, Well, connect the output of number 1 to the input of number 2, and from 1 to 3, and from 1 to 4. So the output of 1 goes to 2, 3, and 4. And then you do it for all of them. And this is all you have to do. And now Mathematica automatically constructs a neural network with this layout. And here we see the net graph. And this is the whole graph. Let me make it a little bit magnification factor. And you see it's quite a complex graph. But if you click on something, you see immediately, okay, this is what it does. It's a vector, 85 elements, that's the input. It has these parameters, it has these internal arrays. If you click on this total layer, that makes the total from the two inputs, you say, okay, it has an output of size 4, it has an input of this size, this is the input and the output port. Any element you can click and you immediately see what are the variables there. It's quite impressive. Let's go back to the original or a little bit higher. There's a website that's called the Wolfram Neural Network Repository. And here you find dozens and dozens of modern networks for audio analysis, for classification, you name it. If you type, you can read them with net model, but if you type net model without arguments, you see all the networks by name which can be called in Mathematica, and you see it's amazing. All of them are there. VCG networks, the networks that work on sounds, ResNet 101, 152, all the networks are right there. But let's have a look at this website again. So here's the neural network. So if you take a network, for example, here we have a Fisher net, you go to the page of that network and you see you can do a download of the notebook, so you have the full notebook into your Mathematica thing, and now you see all kind of network parameters can be set, how you work with it. You give it an image, it says it is a flamingo, so this is a recognition net. You can ask all kinds of probabilities, what properties can you ask, and every network is nicely explained how to use it, how to modify it, and I have a dedicated video on YouTube which in great detail where I explain how to build these neural networks. This, for example, is a network, it's called a UNet, trained on glioblastoma. And this UNet, I just downloaded it. You see it is quite a complex net. And here is the whole UNet. You see it has the UNet shape. And this network is now can be used. It's fully trained. You can surgical operations, you can cut it, you can train it again with your own data. Lots of possibilities, but this neural network website is amazing. Etienne Bernard was for 7 years the developer for the neural networks in Wolfram, and he wrote an outstanding book. It's one collection of notebooks, fully interactive, and this notebook is available on the web, and all the code is for free, and it's the best book I've ever seen to learn neural networks. It's very nicely building up. It tells you everything about transformers, about all the different shapes of network, how to train them, what are optimization technique, what is gradient descent. It's carefully explained step by step, and you can do everything on your Raspberry Pi interactively for free. Well, if you look at machine learning methods, here, for example, let's have a look in the documentation. Machine learning has a lot of classification techniques, decision trees, gradient boosted trees, logic regression. All of it is implemented in Mathematica, and you can use it. Random forests, support vector machines. It's really professional. It's at the highest level you can think of. Here's, for example, k-means. It goes on, and study this by yourself. Suppose I make a random real between 0 and 1, and I make 300 triples. So that means 300 XYZ points. So these are 300 points in 3D space. And now I want to find the clusters in these 300 points. And how do I do this? I take the method k-means, and I find the clusters in these points 3D, and then I show them with graphics 3D by putting a point. You see I have the function map here. I map this function point on all these 300 points, so I get 300 points with a small opacity, 0.1, and I show the convex hull mesh. Let's see what happens. And here we have the convex hull, and you see I can see the 15 clusters of these data sets in 3D, nicely clustered with the k-mean method. But the interactivity, the way that I can, with a single line of coding, immediately have this impressive high-level clustering result, that makes why I think this is 21st century computing. I have never searched for packages because everything is included in Mathematica. It is so complete, that's why it's 1.4 gigabyte. People complain, why is it so big? Well, this searching for packages that I see on the internet, on Medium, on all these websites, it is amazingly slow. It takes so much time, and in Mathematica it's all right there. If you check out the documentation for find clusters, you find all kinds of ways. It's nicely explained here how it works, what does it do. I have not enough time now to go into it, but the distance functions, the features names, the methods, it's incredibly versatile, and all the different means that you can think of. So if you find a paper in which they use a particular method, you can directly implement it and see what the authors in the paper have done. Let's close this, make a little bit of space. And let's have a look at parallel computing. Make it a little bit bigger. Well, you can even do parallel computing on the Raspberry Pi. Let's have a look at how the Raspberry Pi looks like. And we run the command system information. Mathematica is now checking all the hardware and software on the Raspberry Pi, and you see I have this kernel, this one for Linux, and here is this tab parallel. And you see I have 4 processors. So I can do parallel processing on 4 processors. Well, let's try to do that. And we take a long, complex calculation, the calculation of an incredibly high prime number. And there are some famous prime numbers that are called Mersenne prime numbers, 2 to the power of n minus 1. So let's try this one. Okay, this is a prime. So this is one of the Mersenne prime numbers. Let's take another high one. No, this is not. But let's find some really high ones, and we take n. You see here, I have a function again. And we take them from 9600 to 10,000. So that's really high. So these are 400 really high, very long prime numbers. So prime q means it's a function, and we cannot make a question mark here, but q means question mark. This means, is it a prime? 2 to the power of, this is then the slot. And what I put into the slot is, range means from 2. So if I take range 1 to 10, I get 1, 2, 3, 4, 5, 10. And this means map this function on this range. And this guy is also important. This means whatever is in front of it, it's a function. Function can be seen as a kind of a slot machine. You put something in the slot, this is the slot, and you get something out. So if the function is a squaring machine, that you put 3 in, you get 9 out. Well, this is now a function, you put something in, and it says, is it a square? And this means it's a function. I always think that this is a function on the slot machine. This is the one-armed bandit. So it reminds me that this is a function. The slot, you put something in. And let's run it. Let's just see what it does. And now you see Mathematica automatically was launching the kernels. And now you see it's evaluating on these 4 kernels, on 20 items each, what it is doing. And you see it goes quite fast because it runs on all 4 kernels at the same time. Oh, that's interesting. I can have system tools, I have a system monitor. Okay, now you see you have the results, and somewhere there should be a true. Okay, here's a true. But how do I find the position of this true in all of them? Well, I ask, give the position in all these 400 results, or 300 results, 400 results, where there's true, and then add this because I started at that number. And now you see, okay, at these positions I have a Mersenne prime. So this one is a Mersenne prime. It's a really big number. Let's have a look. How big is the number? Wow. That's a very, it's really a prime number. You see, it is an odd number and it's very prime. So this is the way, and this is all running on the Raspberry Pi. But I promised you that I would show that it is really parallel processing by showing that while I run this parallelization command, I look at my CPU activity. And here I have the 4 colors of the CPUs in my system viewer. And now I run this command again. And immediately you see that all the 4 kernels, they start to work at 100%. It's beautiful. And this is really done on a Raspberry Pi. Some of them are now sending the messages, sending the data to the other ones. So some are controllers and some are calculations, but Mathematica takes care of all of that. And as soon as the calculation is over, you see that the kernels all go back to normal. This is really beautiful. So I can now 4 times speed up my calculations by just this simple command, parallelize. You can use this for anything, and Mathematica takes care of all the setting. And of course it has to be parallelizable, but Mathematica takes care of the distribution over the 4 kernels. It has the best symbolics in town. So for example, you take any integral, and it's famous, any integral that almost exists has been built into Mathematica. They're very professional mathematicians on board. So whatever you take, and I really don't know what these functions are, I took them from the example pages. But for example, if you take an integral like this, you know that if you take the derivative of the integral again, so I take now d, that means derivative with x, you get the original function again. So if I take the derivative of this complex thing, you get the derivative. Oops, that's by far not the same. It's quite more difficult. But now you have a function in Mathematica called simplify, and it does all the mixing of the formulas, and you see, okay, square root of x, square root of a plus x, that's exactly this. So with simplify, I get exactly what I had. Well, in SymPy, you cannot do this. I looked at simplify in SymPy, and I looked on the web page of the documentation, so docs.sympy.org, and you see here simplify, and it's pretty amazing, but you see here that x star star 3, there is no mathematical notation. It is very ugly brackets. It's actually amazingly ugly. And then I say, well, in the 21st century, when I do this, and I saw that on Jupyter notebooks, this is now converted into LaTeX, but that's just a conversion. If you want to go from this LaTeX back, like I did here, take the output result and take the derivative again, you cannot. And I checked the SymPy possibilities. They are far less than what Mathematica can do. So no matter what you take, the most complex integrals, it does it. And when you get some very complex result out, for example, here some exponential integral e, well, that's a very odd function, but you can even plot it, and Mathematica says, okay, this is how the function looks like, and you can nicely inspect the function. I never heard of this function, but here you can visualize it. And if you integrate this function, all of them over 0 to infinity, you get 1 over n, etc., etc. But it just says the symbolics in Mathematica are outstanding. Mathematica is quite modern and has a full integration with the OpenAI ChatGPT 4 notebooks. So let's see if we can do an example. I open a new notebook, and now I open a chat-enabled notebook. Now you see we have a cell here that is able to communicate with the large language model GPT-4. So let's give it an example. I made one here. Do a dictionary lookup for all English words. Select those words that are the same as the reverse word and has more than 2 letters. These are palindromes, so words that run backwards and are the same. So we copy this text and we insert it in the news here, and we press Shift, return, and see what it is saying. Okay, we got, it finds dictionary lookup and then reverse words. Let's see if we can run the code, and wow, here we have it. So we have now the possibility to ask for any Mathematica code just by writing in English what we say. And have a look how much it looks like English in Mathematica. Select those words that are the same as the reserved words. So select from those words the words that are, if you put it in the slot, is the same as the string reverse of that word. And this is the Mathematica notation for the Boolean and, if the string length is larger than 1. And this whole thing is a function, a pure function, because we see that we have this symbol function here, and we do that for all the words, and then select them. So it's a very convenient and easy way to generate your code. We don't save this, close this. Oh yeah, and there was a very nice overview written recently by Michael Trott, which I show here, and I recommend to see what are the latest developments in these large language models. Let's give an example into pattern matching. And pattern matching is a very essential part of the Mathematica language. The underscore stands for a pattern. So if I say here x to the power of underscore, it finds all the cases that have something x to the power of something. So let's see. Yeah, only the x square and the x third are now found because they match the pattern x to the pattern of something. If you want to use the what is found itself, you give it a name and you put just the name in front of it. So this is something and it has the name n, and then this exponent is what you want in your matching pattern. So now you say, okay, go look for x to the power of something and then give me back what is the exponent. So now you see we only get 2 and 3. If you want to find cases that explicitly match integers, well, you see there are lots of things here, functions, but now you say something, but now we put to the right, to the left is the name, and to the right is the type. So now we have the integers, and we see right, we get the integers. Here's another nice example. Suppose we take an image, and I could take, I open a browser, and let's say I want an image of a dog. And now I take, for example, this image. I say copy this image, put it here right in my, and now you see I want to have the pixels, so I extract the image data, and now you see they're all triples. So this is the first pixel, and it has RGB values, and then there are 161 of the first line, etc. So there are lots of lines, etc. Mathematica doesn't show all of them, but you see that it's nice enough to do. But now what I want to do is I say replace /point every triple underscore 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 by its mean. Well, I have to give them a name, so I say, okay, I call this R, I call this G, and I call this B, and I make that R plus G plus B, and then I say control slash divided by 3, and then make it a real number. So now what I do, I have all these functions, and now you see there are no triples, but there are now single functions. And if I now have a look, how does pix look like, you already know what happens. I get the black and white value. So just say what you want, replace every triple by, for example, its mean. If you replace it by R, you get the red channel. You can do any change as you like. The message I want to give here is this you do in half a minute, and then you have just say in English what you want. You can replace and bundle and whatever you like, you can do it. Another way to use these things is string search, which is quite powerful in Mathematica. I found this nice website where people were looking at the birthday, and I said, okay, find your birthday in a million digits. I thought, let's have a look in a million digits of pi. So I take here the numerical value of pi, 10 to the power of 6, a million. I put them to a string, so I have all the digits as a string. I want to drop the second digit because that's a dot, the 3.14, etc. So I said the string drop a list of things, and in this list is only one element, the second. So now I have this pi string, and it generates 1 million digits on a Raspberry Pi in less than a second. In Python, and I did that took quite a long time, but I'm not sure if that code was optimized. Some people have even printed pi on a mile of paper. Oh, I don't have it here, but it's quite amazing. They printed it. You see how much fun you can have with pi. Okay, now we go search for my birth date. I'm an old guy, 52, so I have 21 March. It's a nice date, beginning of the spring. And now let's see, hey, 3 times in this million digits, it found my birth date. And this is the beginning and the end of the string, and the beginning and the end of the string. If you want to go for further, and they say, okay, I want to have 10 million, and it sounds quite incredible, but even on the Raspberry Pi, it can be done, and it takes about, I think, 20 seconds. No, 15 seconds. Okay, but that's pretty fast, and this is a Raspberry Pi. So how long is this string now? 10 millions. And if I take the last 10 digits, well, here they are, calculated on a Raspberry Pi 5, 10 million digits. On my laptop, I could create pi to 1 billion digits. It took 30 minutes, and of course that's a much faster thing. And everything is much faster. So if you like this on the Raspberry Pi, but you really want it faster, and many more things like the use of the GPU, which is impressive, especially neural networks, go get it and run it on your laptop. Let's take a few more examples. Functional programming. For example, I have this list here. Well, if you want to count the number of Ds, there are 3 of them. Use the function count. What is the position in the list of the Ds? It's right here. What is the first one? It's right here. If you select from this one, which one is, and I'll have a function here again, and the function puts on everyone, which one is larger than 2, you do this. So you really can speak English. Select from this list the elements, you put them in the slot which are larger than 2. Image collage, of course, makes a collage. What do? I harvest the images from this website, thispersondoesnotexist.com. You make a table of these images, do it 9 times, and you get 9 images. And because it's a little bit too fast, this cannot generate it too easy. Let's make a small pause here, let's say 0.1 of a second. And then this, because I asked too fast for these images again. And now it takes a little bit time in between. Now you see you get 10 different images. You also see that there are some mistakes made. But it's easy now to harvest any images as you like. You can harvest thousands of images with this command. But the naming of functions is really careful. So image collage. And if you want to study everything with images, just type in square root image and then a wildcard, and you get all the image functions, and the same for any function. It's incredibly complete, and you can do whatever you like with these images. And it has the best documentation ever made. That's really for sure. If you click on the documentation, in the documentation you find here in the top, Wolfram documentation. It's worth studying this carefully. It's amazing. You can see data manipulation, visualization and graphics, machine learning, and everyone has tutorials, guides on how to do it on strings and text, graphs and network. It's pretty amazing. I don't have time now to go through all of them, but really take the time to go through this and you will be really amazed. You don't have to search endlessly for packages because everything is available in Mathematica itself. It's 1.4 gigabytes, it's big, but you will be surprised by the richness and tutorial value of this Wolfram documentation. And what is so nice, whatever you click, so for example you have here data manipulation and array manipulation, you name it. Let's take a graphical one. Do some visualization and graphics. I have some data visualization. And for example, you have whatever. The list slice density plot 3D. You always have examples. And if you take, for example, this example, copy it, put it in your notebook, and you just say Ctrl V, run it. Oh, sorry, this is just generating the data. And now we do a list density plot. It's not the most spectacular example, but it is just to show you that the guide itself, everything is a Mathematica expression and can just copy paste. And what is faster than this? So have a look. The help is in the top, and here you see, for example, numerical operations on data. It's amazingly complete. Curve fitting, descriptive statistics, discrete distributions, all of it is in there. And then one by one, you see all these functions carefully explained, and they all have long names. They all have the names quantile and interpolation, continuous. Here you see harmonic mean. Nothing is abbreviated. It is really what you want. So if you search for this, you find it. And here you see all the different things. It's very nice to study this. As a kid, I loved to read the encyclopedia. Well, I love to read Wolfram's documentation as well. I learned so much. It's incredible. And because you can do it immediately, you learn by doing it. And this documentation has over 150,000 examples. So you will be amazed at this huge and professional world. And it's very versatile. You have computing, chemistry, geographics, finances, system modeling. No time to go through it, but I will make some videos that cover this, especially on deep learning and visualization. And if you want to see more, go to this website and you'll find all the description of it. It's very nicely done on the professional website. What is really nice for Raspberry Pi users is the Wolfram Demonstrations project. Over the years, many users of Wolfram's Mathematica have made demonstrations, and there are more than 13,000 demonstrations here in any topic on business, creative art, kids and fun. And it's just beautiful. Just click on one and you can play with the interactive visualizations. It is just amazing. It is beautiful. Find anything. If you want to find what is the closest tour between the 30 largest cities in India, well, there is a demonstration for it. It's just beautiful. Have a look. And the most stunning thing when I thought, why is nobody looking at Mathematica? Because people think, and I see that on lots of web pages, it is expensive. Well, it's not expensive at all. If you, for example, see that it is €75 per year, $75 per year for university students, or for any students, you get 2 activation keys. It's not expensive at all. And for many students, the university has a site license, so you can get it for free. For example, if you look on this website, site info, suppose I type my email address, at TUE Technical University Eindhoven.nl. I agree with this. Now it checks. They say, hey, Technical University Eindhoven has access to Wolfram products. And I'm a faculty staff, or I'm a student. And then you can just go log in. And then you log in to your Wolfram Mathematica account number. You use your email address and you get it for free. And you can download Mathematica desktop. So if I do this, you see I have to log in into my account. It checks my email address and I can download the version for free on my Mac, on my Windows machine, on whatever I have. If you don't have this, it's really cheap. So for €75 per year, you have it. It's only €6 per month. You have it on your big laptop, which is much faster than this Raspberry Pi. If you cannot afford this, you can stay with your Raspberry Pi. And I can recommend use it on your laptop as well. It is quite impressive if you speed up everything that you see. And for personal use, if you have no affiliation to university, it's only €200 a year. And of course, it's for free on the Raspberry Pi. If you want to just test it, you can try it for free for 15 days. And if I see how much people spend on, for example, Python, if you look at Udemy, a very rich course set, and you see the net value, Udemy has a market cap net worth of 2.25 billion. Well, that's pretty impressive. So where's all the money going? This is not going to the Python organization, but it is to the people who organize courses. If you can do the same, Coursera, millions of people spent 20, 30, 25 euros a month for all kinds of courses. And of course, these courses are incredibly valuable because they give you jobs and they give you diplomas. But to learn coding, for example, if you're not into computer science, but if you're, for example, a neuroscientist, or you are in finances, or you're an artist, then I think this 21st century computing is quite amazing. A few last items before we close, just for Raspberry Pi lovers. This is the way how to use a USB webcam. You can just plug in the webcam into the USB and then say open device camera. Mathematica has all the drivers, and you see it is now connected to my Logitech Pro webcam C920. And if I ask for the current image, you see me smiling. But if I do, for example, dynamic as a function, and that means keep doing it, you see me and it's real time. So now we have video on the fly. So this is a very nice way. But you can use all the Mathematica statements. So suppose I take the current image and I take them in pairs. So each time I take 2 and I take the image difference dynamic all the time. Now I get all the time the difference. So you see, only when I move my head or move my hand, as long as I keep them silent, there is nothing. Well, this is actually what every camera uses in motion detection. Just take the difference, and you see everything is now a one-liner in Mathematica. You can even go a step further and you say, okay, we have the current image and we have the function find faces, and then highlight it and do it in dynamic. So now it automatically finds the faces. It needs to download a neural network, and you see this is my my face, and if I move, it follows my face. It's pretty cute. And all this, you can put any function of Mathematica in here and do real-time computing with your video. And at the end, you just close the device, and now the device is closed. There's a lot of information in using connected devices, and you see here that it will talk to lots of the GPIO, general purpose pins, to Arduino camera. It has lots of connections, and check them out. Lastly, there's a large community in Mathematica, the Mathematica world. It's also called the Wolfram language because people realized that Mathematica was too often related that people thought it must be mathematics only, but it is not. So it's now called the Wolfram language, but it's essentially the same. And there is a large Wolfram community, and this is interesting to study. There are lots and lots of people, and they have contributions on all kinds of topics. Really see these discussions. The staff picks are particularly nice because they have some more general applicability, and there are endless discussions, solutions on all your problems. It's a really nice world to explore. And this is huge. The Wolfram demonstration project that I already showed before, it's definitely worth trying it out. The Stack Exchange is for Mathematica. You can find all kinds of questions answered here. It's the same as in the Python and Julia and R world, etc. And here you see for Mathematica and the Wolfram language exactly the same. And check it out if you want to find answers to your questions. And Wolfram Resources is the website that combines them all, and Wolfram has done a really good job. And here you find lots and lots of places to study in the different fields that you like, interactive courses, courses on finances, you name it. We've come to the end, and I want to do some personal statements. Why was I, during a long career, so happy with Mathematica? Why made I this small overview? Well, I found during all these years that the code is particularly elegant. If I see this code, that was for me always really difficult to maneuver through. But if I looked at Mathematica and saw everything is plain English, well defined, it's not easy to understand. You need time to really understand it. Once you have it, and I think if you follow the videos that I'm going to make and you study carefully, step by step, all these things, you will develop a nice way learning how to code. But I was particularly pleased by the time that it saved me, that I didn't have to look for all these ill-named and undocumented packages, but I found every function directly in Mathematica, professionally tested, optimized for speed, and well-named. And I could do everything I wanted, from the most complex image processing, data analysis, neural networks, and I could implement it fast. If a paper came in, I had an implementation within the same day. And I think the price of Mathematica is fully justified, as it is for all professional services. Open source, of course, it's fine. It brings the world to a large audience, but for me, it is paying for professional services, like as I showed in the beginning, for Microsoft, for all the services that I have for web design. It's like buying at a supermarket. You pay, you get controlled quality, service and information, and that's exactly the same. And Mathematica, as I showed you, is not expensive. It's for free on the Raspberry Pi. It's for free for many, many students at universities. Only 75 euros a year, and for that money, I think you get really 21st century coding. And the code is so well designed that I could use it for decades. And my notebooks that I maintained over all these years are still running. Mathematica kept inventing all these years. I was at many of the Mathematica conferences and saw the progress, and it kept being impressive, really. And now I see how many of these inventions are slowly emerging in the open source software. So I see slowly pattern matching, functional programming, notebooks, they all become accepted, but I use them already for decades, and that's really impressive for Wolfram that it was designed so well. In this video I could only show you the tip of the iceberg. I hope you found some directions and idea and will embark on a further journey. I showed you many nice directions in the Mathematica website. The next step you could take is a gentle introduction to 20th century coding, which would take lots of steps that I had to take too fast in this video. And also check out the other videos on my YouTube channel at 21st Century Coding and subscribe. Thank you very much. See you in the next videos.